Okay, this is part 3 of notes 3.3. This question, I just read it, it's actually pretty horribly written. If let's go ahead. This first one's conceptual, so let's read through it together. Beaker A contains 100 gram sample of water. The delta H of vaporization is 2260. And beaker B contains a 100 gram sample of ammonia. The delta H is 1369. If both beakers are heated at the liquid's boiling points, which will dry first? This is terribly written. Which will, you can just cross that off and say boil off first. Okay, so that's what they're asking. They're saying, hey, look, we've got, I'll just draw it real quick here so you guys can see. Here's a 100 gram sample of, this is 100 grams of H2O, and over here we've got a 100 gram sample of ammonia, NH3. Okay, ammonia is NH3. Delta H of vaporization for this one is 2260, and that's beaker A. That's beaker A, and beaker B, which is ammonia. Delta H vaporization is 1369. Okay, they're going to boil both of these beakers. No, let me do this. Delta H vape. Delta H of vape. Okay, so they're going to boil off both of these beakers. And they want to know which one's going to boil first. Well, the number that's got the lowest number here, all that tells you is that's less heat required to boil this thing. Less heat energy is needed to boil this off. So if we add this, if we put this both onto a boil, which one's going to boil first? Well, that one's going to boil first because it doesn't require as much heat. And secondly, it's going to boil off faster because it doesn't require as much heat for the vaporization. Okay? That's how you have to look at this. So which one's going to boil completely first? It's going to be this guy right there. Why? Because the delta H of vaporization tells us less heat is required to vaporize all of this off. Okay? So I'll go ahead and pause this, and you can write something. You can either copy this completely, or I'll post it on. I'll post it online right now. Okay, which liquid has stronger attractions between their particles, and explain. Okay, well, the reason this is higher is because the attraction between the particles is stronger. So it requires, the stronger the attraction between the particles, the more heat is going to be required to cause this thing to change states. Okay, so this has a higher delta H of vaporization because more heat is required. Because the particles have a stronger attraction between them. That's why the delta H of vaporization is stronger. These particles here, the strength between them is not as strong, hence the lower delta H of vaporization. And you can write something like that, and I'll let you copy this, and you can, I'll pause. Okay, next up. For water, the delta H of fusion is 334 joules per gram, and the delta H vaporization is 2260. Write a chemical equation for the melting of ice. How much energy is required to melt 20 grams of ice at 0 degrees Celsius? Well, you can look back in your notes if you want, but the melting of ice looks like this now. Just think it through carefully. You've got ice, which is H2O solid, turns into H2O liquid. And where do I put heat? Well, I have to add heat over here. Okay, there's your chemical, oops, sorry, H2O. That should be heat. Okay, heat plus solid H2O yields liquid H2O. How much energy is required to melt 20 grams of ice at 0 degrees C? Okay, when you get these questions, here's the formula that you have to use. It's very, very simple. Q equals M times delta H. Okay, again, it's right here. Q equals M times delta H. All right. And let's go ahead and do this. Q equals M equals, and delta H equals. So they're asking us how much energy, so that's going to be Q, is required to melt 20 grams of ice. So that's your 20 grams is M for mass. 20.0 grams at 0 degrees Celsius. Okay, so that's telling us that we're at the point of fusion. Okay, and we're melting now. We're melting, so we're going to have to add our delta H is going to be positive, right? Because we're adding heat into that. If I'm not mistaken. Yes. So we're going to use the positive delta H of fusion, which is going to equal 334 joules per gram. All right. 334 joules per gram. Let's go ahead and solve now. Q equals M times delta H, which is going to equal the following. 20 grams times 334 joules per gram. And that's it. That's all you gotta do. Cancel out grams, and when you do that math, you get 6680. Oops, 6680 joules. Okay, 6680. That's all you gotta do. It's a lot of stuff, but the math actually is pretty easy, and the formula is actually easier than the one we did before. Write the chemical equation for the condensation of water vapor. How much heat is released to condense 20 grams of water vapor at 100 degrees C? Hey, there's a little hint here about whether your delta H is going to be positive or negative. Okay, how much heat is released. So if you see that released, right off the bat, you should be thinking negative. But let's go ahead and write everything out. Write a chemical equation for the condensation of water vapor. Okay, so we're going from H2O, condensation, H2O gas, to H2O liquid. Now the next question you ask yourself, where do I put heat? If I put heat on this side, I'm just heating up gas, so that doesn't make any sense. If I'm adding heat to gas, it's still going to be gas. So my heat is definitely going to be over here. That's going to be your formula. Okay, that's going to be exothermic, although they didn't ask that. And here's the formula you're going to use to solve. Q equals M delta H. Okay, so we're solving for Q. How much heat's going to be released? Condense 20 grams of water at 100 degrees Celsius. Your delta H of vaporization, 2260. Negative, right? Negative because we're losing heat. Okay, so it's going to be negative 2260 joules per gram. That's it. Now that's the hard part. Now you just multiply everything out. Q equals 20.0 grams times negative 2260 joules per gram. Cancel that out. And that's going to equal 45,200 joules. Negative. That's going to be negative 45,200. Yeah. And your Q is going to be negative as well. Your Q value will be negative, and that's all good. All right. Negative means we lost heat. We lost energy. Again, why did we lose energy? We're going from gas. We're losing energy. We're going from gas to liquid. Hey, this thing comes in handy. You can use it on a test to follow this. Go, am I adding energy or am I losing energy? If I'm losing energy, or if I'm going from gas to liquid, that's a loss of energy. Liquid to gas, I'm adding energy, right? If I'm losing energy, exothermic. Adding energy, endothermic. Okay, that's how this thing works. It's very, very handy. That concludes notes 3.3.